I've spent the last month building out STEM labs in three very different homes. One family handed me a spare bedroom, another gave me the corner of their garage, the third, a dining room that had to stay a dining room. And every single one of them told me the same thing. They didn't want toys that get used once and shoved in a closet. They wanted real tools their kids would actually come back to. My name is Kazuki Tanaka, and I test learning equipment for a living.
Welcome to the STEM Lab podcast. Quick thing before we jump in. Everything you're about to hear, the research, the testing data, the script, that's all human verified and written by real authors. The voice delivering it, that's AI generated. Just want to be upfront about that. If you've been listening for a while, thank you, seriously. And if this is your first episode, glad you're here. We drop new episodes every Monday, Wednesday, and Friday, covering the tools and techniques that actually move the needle for home STEM learning. Now, here's what we've got for you today. After running dozens of projects through these spaces, I can tell you exactly what works. The best STEM lab equipment for home learning builds measurable skills through repeated use, supports progressive complexity, and earns its footprint with concrete capability, not vague promises about creativity or problem solving, actual capabilities you can point to. Let me walk you through what to look for, then I'll show you the specific gear that delivered. Now, the first thing you need to understand is progressive skill development and expandability. The best home lab equipment grows with the learner. I'm looking for systems that start simple but unlock advanced features as skills develop. Take a quality robotics platform. It should support visual block coding at first, then transition to text-based languages like Python or C++. The LEGO Education Spike Prime set does this perfectly. My test group started with drag-and-drop programming. 6 months later, they were writing custom Python functions. Check the link below to see the current price. But also check for hardware expandability. Can you add sensors, connect multiple units, interface with industry-standard platforms like Arduino or Raspberry Pi? I've watched too many families hit capability ceilings with closed ecosystems. Real learning happens when you can say, "What if we tried this?" and the equipment doesn't block you. Next up, lab specs: power, connectivity, workspace requirements. Before I recommend anything, I measure actual power draw and workspace needs. A 3D printer might claim a 12 by 12 inch footprint, but you need clearance for filament spools, maintenance access, adequate ventilation. I spent 3 days mapping the real space requirements for common home lab setups. Power considerations matter more than most guides admit. Running a 3D printer, soldering station, and laptop at the same time can trip a 15-amp circuit. I learned this the hard way during a weekend workshop. Look for equipment that operates on standard 120-volt household power and note the amp draw. Battery-powered options reduce infrastructure requirements but add the recurring cost and complexity of charging logistics. Connectivity splits into 3 categories. Standalone operation is best for younger learners and power-sensitive environments. USB connected requires a dedicated computer but enables more sophisticated programming. Wi-Fi or cloud-dependent offers remote monitoring and software updates, but fails without internet access. For home labs, I generally recommend USB-first designs with optional Wi-Fi. You get reliability with connectivity when you want it. Moving on to technical compatibility and software ecosystems. Nothing kills momentum faster than software compatibility nightmares. I test every piece of equipment on Windows 11, Mac OS 14, and when it's relevant, Chrome OS. The reality, most cross-platform claims mean works on Windows, maybe works on Mac with driver wrestling. Good luck with Chromebook. Programming environment compatibility determines long-term value. Can the equipment work with Scratch, Python, and Arduino IDE? Does it require proprietary software that might disappear in 3 years? Or does it support open-source tools with active communities? I've restored function to 5-year-old equipment in my fabrication lab because it used standard protocols. Proprietary systems become expensive paperweights. Check whether the platform requires cloud accounts, sends usage data, needs ongoing subscriptions. Some robotics kits require annual software licenses. That's not necessarily a deal breaker, but families deserve to know the total cost of ownership up front. Now, let's talk about durability for repeated use and repair economics. I subject equipment to abuse testing that simulates 2 years of regular home use compressed into 3 weeks. Components get assembled and disassembled 50+ times. Projects run for extended hours. Parts get dropped from table height onto concrete, accidentally in realistic scenarios. The question isn't whether things break, it's what breaks and whether you can fix it. Quality equipment uses standard fasteners, provides replacement part access, includes clear documentation. I can fix my Creality Ender 3 V3 SE with parts from 3 different suppliers. Check the link below to see the current price. Proprietary designs with custom components become expensive repairs or total losses. Material quality shows up in long-term testing. Thin ABS plastic housings crack, weak solder joints fail, cheap bearings develop slop. I track failure modes across 200+ hours of use, because that's the difference between equipment that serves multiple children across years versus gear that disappoints after the first intensive project. And finally, skill outcomes and career pathway alignment. Every piece of equipment in a home lab should answer this: what capability does this build? I'm not talking about vague creativity or problem solving, I mean specific, measurable skills. A quality oscilloscope teaches signal analysis, troubleshooting methodology, measurement techniques used in every electronics career. A hobbyist meter teaches checking batteries. Both measure voltage, but one builds professional competencies. Look for equipment that mirrors industry tools. Learning Arduino IDE prepares students for embedded systems development. Mastering FDM 3D printing translates directly to rapid prototyping workflows in engineering firms. I spent 8 years in product development. The skills gap between toys and tools is massive, but several home lab equipment options bridge it successfully. All right, here are our top picks. First, the Creality Ender 3 V3 SE. Best entry-level FDM 3D printer. This represents the current sweet spot for home fabrication capabilities. I've run this machine through 200+ hours of print time across 3 different home lab environments, and it consistently delivers usable parts without the maintenance headaches of earlier budget printers. Check the link below to see the current price. Here's what works. Auto bed leveling actually works reliably. I tested it across 50+ power cycles. It prints directly from USB, SD card, or Wi-Fi without cloud dependencies. Uses standard 1.75mm PLA filament readily available for $15 to $20 per kilogram. The build volume is 220 by 220 by 250 millimeters, handles most educational projects. Active community support, replacement parts widely available. The direct drive extruder handles flexible filaments for advanced projects. Works with Creality Print and Ultimaker Cura slicer software, both free, Windows, Mac, and Linux. Here's what doesn't. The exposed heated bed requires clear safety protocols with children under 12. The stock build plate requires cleaning between prints with isopropyl alcohol, adds 2 to 3 minutes per session. Wi-Fi connectivity gets flaky on 5 GHz networks. Use the 2.4 GHz band or just stick with USB. Lab specs: requires 350 watts at 120 volts under 3 amps. You need a 20 by 20 inch workspace including filament clearance. Operating temps are 60 degrees Celsius bed, 220 degrees Celsius nozzle. Budget $30 a month for filament at moderate use. That's 2 to 3 prints weekly. Skill outcomes: TAD to physical part workflow, support structure strategy, print parameter optimization, basic maintenance protocols. Prepares learners for Fusion 360, SolidWorks, professional additive manufacturing environments. Next, the Alegu Arduino Mega Complete Starter Kit, industry standard microcontroller platform. This includes everything needed to transition from visual programming to embedded systems development. I tested this against 4 competing kits, and Allegu's component quality and documentation proved significantly better than the budget competition. Check the link below to see the current price. What's good? You get an Arduino Mega 2560 microcontroller with 54 digital I/O pins and 16 analog inputs. Over 200 components, including sensors like ultrasonic, temperature, motion, plus motors, LCD display, breadboard, tutorial book with 35 projects from LED basics to LCD menu systems. Compatible with Arduino IDE, that's C++, Scratch for Arduino, and Python libraries. The breadboard design teaches circuit principles without soldering initially. All components are reusable across custom projects. This is a toolkit, not a one-time kit. Works offline, no cloud dependencies or subscriptions. What's not? The learning curve is steep for students without block coding experience. Plan 3 to 4 guided sessions before independent work. Component organization requires a separate storage solution. I recommend a tackle box. Power supplies included, but some projects drain 9-volt batteries quickly. Budget $15 a month for intensive use. Lab specs: USB powered for programming and testing, external 9 to 12 volts for autonomous projects. Requires a computer with USB-A port. Adapters available for USB-C only systems. You need about a 24-inch desk area with laptop. Ages 12 and up recommended, 10 and up with adult guidance. Skill outcomes: digital and analog I/O, sensor integration, motor control, serial communication, embedded C++ programming fundamentals. Direct preparation for university-level engineering coursework and IoT development. This platform bridges nicely from visual programming environments to professional embedded systems tools. Now, the National Geographic Rock Tumbler Kit, Geology and Material Science Fundamentals. This one surprised me. I initially dismissed rock tumblers as low-value equipment, but 3 months of testing revealed legitimate material science learning opportunities. Plus, it operates independently, freeing up workspace. Check the link below to see the current price. Here's why it works. The 4-week tumbling cycle teaches patience and process observation. Progressive grit stages, coarse, medium, fine, polish, demonstrate controlled abrasion. Includes 1 pound of rough specimens plus grit refills for 3 to 4 cycles. Runs autonomously for 24 to 48-hour intervals, doesn't monopolize lab time. Real geology. Identifying crystal structures, hardness testing, mineral properties. Quiet enough for bedroom installation, 45 decibels at 3 feet. Optional gemstone mining rough available for expandability. The downsides: initial cycle requires 4 weeks for results. Delayed gratification challenges some learners. Consumable costs run $12 to $15 per cycle for grit and polish compounds. Barrel leakage if you overfill it. I learned this on cycle 6. Mark the fill line with permanent marker. Lab specs: requires a 120-volt outlet and a 6 by 6 inch footprint. Runs continuously during cycle phases, so plan installation near a water source for rinsing operations. Water and grit disposal must be discussed. Don't dump abrasive slurry down drains. Ages 8 and up. Skill outcomes: material properties, Mohs hardness scale, mineral identification, multi-step process management, data recording across extended time frames. Complements physics and chemistry curricula, provides tangible examples of crystalline structures and material transformation. Next is the Rigol DS1054Z digital oscilloscope, professional measurement capability. This is the controversial pick on this list. It's expensive for home equipment, typically around $350 to $400. But I've watched it unlock electronics comprehension that multimeters can't touch. After using one in my fabrication lab daily for 3 years, I recommend it for families serious about electronics pathways. Check the link below to see the current price. Why it's worth it.
50 megahertz bandwidth, 1 gigasample per second sampling rate handles most educational signals. 4 channels enable circuit comparison and complex signal analysis. Professional UI matches equipment in university labs and engineering workstations. USB storage for waveform capture supports remote data logging. You can unlock it to 100 megahertz bandwidth through community firmware. That's a gray area, but it's widely practiced. Built-in protocol analysis for I2C, SPI, UART decoding. No subscription, fully offline capable. The challenges. Learning curve requires structured guidance. Plan 6 to 8 hours of instruction before independent use. Probes need careful handling. Replacement probes run $40 to $60 per set. Screens smaller than screenshots suggest. 7-inch diagonal takes adjustment if you're comparing to bench oscilloscopes. Lab specs. Standard 120-volt operation, 13.5 by 5.5-inch footprint plus probe storage, ages 14 and up recommended, 13 and up with electronics project experience. Pairs with Arduino and Raspberry Pi projects, no consumables beyond occasional probe replacement. Skill outcomes: signal analysis, frequency and amplitude measurement, circuit debugging, timing diagram interpretation, analog-digital conversion concepts. This is the measurement tool professional engineers use. Mastering it provides direct career skills. Students gain capability to diagnose circuits independently rather than guessing at problems. Moving on to Snap Circuits Pro SC500, Progressive Circuit Design Platform. This remains my recommendation for ages 8 to 12 transitioning from simple kits to actual circuit design. I've tested this through 150+ assembly cycles across 2 home labs, and the snap-together design holds up significantly better than breadboard alternatives for younger builders. Check the link below to see the current price. The pros: 500+ experiments from simple switches to FM radios and digital logic. Color-coded components snap onto a grid base, no soldering or breadboard frustration. Project scale from 10-minute builds to multi-day installations. Includes programmable sound chip, photosensor, relay modules. Real components, not simplified analogs. Clear schematics teach symbol reading and circuit documentation. Expandable with additional Snap Circuits modules. Compatibility across the entire product line. No consumables, all parts reusable indefinitely.
The cons. Snap connections occasionally require adult finger strength. That's the trade-off for durability. Limited to included components, you can't add arbitrary sensors like Arduino platforms. Storage becomes chaotic without an organization system. A bead organizer box solves this for about $12. Lab specs. Battery-powered, 4 AA batteries for most projects. No electrical outlet required. Portable. 18 by 12-inch workspace is sufficient. Ages 8 to 14. Can engage younger children with supervision. No software requirements. Skill outcomes. Series and parallel circuits, transistor switching, logic gates, oscillator design, relay control. Bridges toy electronics kits and breadboard prototyping. Prepares learners for schematic reading and circuit analysis. Prerequisite skills for Arduino and Raspberry Pi projects. Consider this part of a progressive electronics learning path that leads to microcontroller platforms. And finally, the Andonstar AD407 digital microscope. Precision inspection and documentation. This fills a capability gap I didn't appreciate until running soldering workshops with students ages 10 to 16. Being able to inspect solder joints on a 7-inch screen transformed quality control from guesswork to objective assessment. Check the link below to see the current price. What makes it valuable? 10 to 300x magnification with sharp 1080p image quality. 7-inch integrated display, no computer required for inspection work. Adjustable LED ring light with angle-dependent illumination. HDMI output supports classroom projection or recording for documentation. 270-degree rotating arm enables PCB inspection and 3D object examination. SD card storage for photo and video capture. Documentation habits start early. Works with soldering, circuit assembly, 3D print analysis, biology specimens. The drawbacks. Magnification adjustment gets finicky at high zoom levels, 200x and above, requires patience. Included stand is adequate but not robust. Aftermarket aluminum stands are available for about $35 for heavy use. Lighting angle is critical for good imaging. Expect a learning period. Lab specs. USB-C power, included adapter or power bank compatible. 12-inch vertical clearance, 8 by 8-inch footprint. No computer required for basic use. Optional HDMI capture with PC for recording sessions. Ages 10 and up. Skill outcomes. Quality inspection methodology, documentation practices, troubleshooting micro-scale assembly errors. Complements soldering, 3D printing, and circuit work. Professional technicians use similar tools daily. This teaches inspection discipline that separates good work from "it looks okay, I guess" work. Now let's hit some frequently asked questions. What equipment should I buy first for a home STEM lab?
Start with a microcontroller platform like the Allego Arduino Mega Kit I just reviewed. It delivers the widest range of project possibilities for around $80 to $100, requires minimal infrastructure, just a laptop, and teaches skills that transfer directly to advanced platforms. I've seen families waste significant money on specialized equipment that gets used for 2 projects, then sits unused. Microcontroller platforms support dozens of project types, motors, sensors, displays, data logging, so they justify their footprint through repeated use. Once your learner has completed 8 to 10 Arduino projects and hits capability limits, then you'll have specific evidence for what to add next. How much should I budget for a basic home STEM lab? Plan for around $400 to $600 initial investment, covering core equipment. Microcontroller starter kit, $80 to $100, basic 3D printer, $200 to $250, measurement tools like a quality multimeter, $50 to $75, safety equipment, including ventilation fan and fire extinguisher, $50 to $75, then budget $30 to $50 monthly for consumables, filament, components, batteries, project materials. I track spending across the home labs I've equipped, and families who budget monthly consumable costs sustain engagement far better than those who make one large purchase then ration materials. The real cost isn't the equipment, it's the ongoing stream of project supplies that enable experimentation. Do I need separate equipment for different age groups? No, but you need equipment that scales. The Arduino, 3D printer, and oscilloscope I recommended all support progression from supervised beginner projects through independent advanced work. What changes is the supervision model and project complexity, not the core equipment. My fabrication lab uses the same Ender 3 printers for 10-year-olds printing simple designs and 16-year-olds prototyping multi-part assemblies. The difference is in print parameter control, design complexity, and maintenance responsibility. Age-specific kits often create capability ceilings. Instead, invest in professional-grade equipment with appropriate safety protocols and adjust project scope to match skill level. What safety requirements matter for home STEM lab equipment?
Focus on 3 critical systems. Ventilation. 3D printer emissions and soldering fumes require active exhaust or HEPA filtration. Electrical safety. Dedicated circuits for heavy equipment, no daisy-chained power strips, GFCI protection in areas with water access. And thermal protection. Heat-resistant work surfaces for soldering. Clear safety zones around 3D printer heated beds, appropriate fire suppression within reach. I've built labs in bedrooms, garages, and basements. Ventilation consistently matters most and gets overlooked most often. A 200 CFM inline duct fan with activated carbon filter costs around $60 to $80 and handles printer emissions in a 150 square foot space. Never compromise on fire extinguisher access. I mount a 5-pound ABC extinguisher within 10 feet of every workspace. How do I know when to upgrade or expand equipment? Upgrade when current equipment blocks specific capabilities you've identified through actual project needs. I see families upgrade too early, driven by "what if we want to" rather than "we're currently limited by." If your learner has attempted 3 different projects that all hit the same constraint, build volume on the 3D printer, I/O pins on the microcontroller, measurement bandwidth on the multimeter, that's evidence for expansion. The oscilloscope I recommended typically makes sense after completing 15 to 20 Arduino projects, when signal debugging becomes the bottleneck. The rock tumbler adds value when geology interest sustains beyond 2 library books. I tell families your first year of home lab should involve maxing out the capabilities of core equipment, not expanding the inventory. Deep competency with 3 tools beats surface familiarity with 10. So here's the verdict. The best STEM lab equipment for home learning spaces balances immediate accessibility with long-term capability growth. The platforms I've recommended here, from the Ender 3's fabrication capabilities to the Arduino's programming foundation to the Rigol's professional measurement tools, they all share common traits. They support progressive complexity, use industry-standard software ecosystems, provide clear skill outcomes, and justify their cost through repeated use across years. I prioritize equipment that mirrors professional tools over educational versions. The capability ceiling matters. Your learner shouldn't outgrow equipment in 18 months. They should grow into it over 3 to 5 years. For most families building a home STEM lab, I recommend starting with the Arduino kit and adding equipment based on demonstrated interest and project-driven needs rather than trying to build complete capability immediately.
Based on my testing across 3 different home environments, the equipment I've detailed creates a capable learning space in 100 to 200 square feet, enough room to support serious skill development without dedicating an entire room. The key isn't having everything, it's having the right foundations and knowing what capability each tool unlocks.
That wraps up this episode of the STEM Lab podcast. Thanks for listening. We've got new episodes coming your way every Monday, Wednesday, and Friday. If you got something out of this one, I'd really appreciate it if you'd leave a 5-star rating and a quick review. That's genuinely how other people find the show, and it helps more than you'd think. And hit subscribe or follow so you get notified the second a new episode drops. See you next time.